I'm Zemeng Zhang from IST 707. Today I'm going to talk about the search engine and AI ML. We have content like this. First starts with some pre-questions and two theories, LTR theory and natural language understanding. Finally, we'll talk about the search engine model, BERT. Let's start with some pre-questions. So we know every day people use search engine like Google, Bing. We enjoy the convenience and efficiency given by the search engine. However, have you ever thought about the essence of search engine? Now I'm going to demonstrate the brilliant mind behind them. How does our computer return the best match of search engine? How does our computer understand your intent? Let's go to learning to rank. So learning to rank is a class of techniques that apply supervised machine learning to solve ranking problems. There is a difference between LTR and traditional supervised machine learning. Traditional machine learning solves the prediction problems like classification or regression on a single instance at a time. For example, if we are doing a spam detection on email, we will look at all the features associated with the email and classify it as a spam or not. The aim of traditional ML is to come up with a class or a single numerical score for that instance, while LTR solves the ranking problems on a list of items. The aim of LTR is to procedural optimal ordering of those items. As such, LTR does not care about what exact score is, but cares more about the relative ordering among all the items. So how does LTR work? There are three approaches of LTR. The first is pointwise approach. So it assumes that each query document pair in the training data has a numerical ordinal score. So we could just apply regression or classification algorithms on it. The algorithms like anything that deals with regression or classification problems is okay. And the pairwise approach, in this case, the learning to rank problem is approximated by classification problem. So learning the binary classifiers that can tell which document is better in a given pair of documents. This goal is to minimize the average number of inversion in rankings. Algorithm using pairwise approach like RankNight, Lambda Rank. And the last approach is listwise approach. These algorithms try to directly optimize the value of one of the above evaluation measures, average overall queries in training data. This is difficult because most evaluation measures are not continuous functions, which is respect to ranking models parameters. And so continuous approximations or bound on evaluation measures must be used in listwise approach. And some algorithms using the listwise approach is like soft rank, ListNag, other rank, and lambda rank. They altogether called the lambda mart. So the major application of LTR in search engine is it is used as a ranking system. And the ranking system outputs the search result directly, just like the diagram shows. Now we're going to talk about the natural language understanding. So natural language understanding is a branch of artificial intelligence that uses computer software to understand input made in forms of sentences in text or speech format. And as we all know, it is difficult for machine to understand the true meaning of sentences. So, sometimes it's even harder for human being to understand what is the true meanings of the sentence. So this is called like lexile ambiguity. It is described as words with multiple meanings combined to make ambiguous sentences and phrases, becoming increasingly difficult to understand. And there's another challenge for NLU as polysemy and homonymy. Polysemous words are words that with two or more meanings, like the verb get. I can see I get you means I know you, or I will get you some food means I will provide you some food. The word get have several meanings, like to procure, to acquire, to understand. And homonym, another main type of word with multiple meanings. We can try to solve the challenges, try to solve the problems using computational linguistics. And for now, in physical linguistics, we know words and concepts living together in nearby space in text are either similar or related. Based on this theory, we could find two major ways of computational linguistics. The first one is word embedding. Is to define the similarity, the relatedness, co-occurrence, to define the environment surrounding the specific word. And based on the environment, we try to find the true meaning of that word. Another one is part of speech. It's an important part of computational linguistics too. It is designed to teach neural net human language concerning map words in training documents to different part of speech. And this part of speech included like nouns, adjectives, verbs, and pronouns. And try to understand the human language. The context is everything. The key problems to handle with NLU problems is for model to learn the context of a specific word. So how does the algorithm learn the context? The first method is word embedding. The word embedding model provided by word to vectors knows the word somehow live together, but doesn't understand what is the context should be. Like the word bank, it could mean river bank or bank deposit, and the machine will recognize the bank as a river bank when a word river comes before the bank. And there's another algorithm called RNN, it's recurrent neural networks. While in this algorithm, it has a unidirectional nature, which means the context window contains the target word and the context word around it to the left or to right. It only goes in one direction, so the words after the target words are not yet seen, so the whole context of the sentence is incomplete until the very last word, which carries the risk of some contextual patterns being missed. Like if I want to fill I made a bank deposit into the blank. We only know the bank does not mean river if we see the deposit behind. So this is not enough for searching engine, so we come up with a better model, which is Google BERT. And Google BERT is the latest search algorithms to understand the natural language. It is Google's neural network-based technique for natural language processing with pre-training BERT. BERT stands for bidirectional encoder representation from transformers. And why do we use BERT? Because BERT helps better understand the neurons and the context of the word in search, and better match those queries with more relevant results. And there's an example. So in one example, Google said with the search of 2019 Brazil traveler to USA need a visa. The word to and its relationship to the other word in query are important for understanding the meaning. So we can see that previously Google would not understand the importance of this connection and would return the results. It's about US citizen traveling to Brazil. While with BERT, search is able to grasp the neuron and know the very common word to actually matters a lot here. So the Google can provide a much more relevant result for this query. Like it provided embassy consulates in Brazil. So how does BERT work? There are several elements that make BERT so special for search and beyond. Several of the special features can be found in BERT's paper title. So it's like B for bidirectional, E for encoder, R for representation, T for transformer. And there are also some interesting development BERT brings to the field of natural language understanding. This includes pre-training from unlabeled text, bidirectional contextual models, and the use of transformer architecture, masked language modeling, focus attention, and so on. Now we're going to focus on two of them. They are pre-training from unlabeled data text and masked language modeling. So the magic of BERT is its implementation of bidirectional training on an unlabeled corpus of text before it is input to the BERT model. Like here is the training part before it is in the BERT model. Since for many years in the field of natural language understanding, text collections had been manually tagged up by teams of linguistics assigning various parts of speech to each word. So the prior model had required manual labeling and the building of distributed representation of words, like some word embedding and word vectors experience, or need a part of speech taggers to identify the different types of word present in the body or of a text. So these parts approaches are just like the part of speech tagging we mentioned before. But BERT learns the language from understanding a text coherent from this large body of content in plain text, and is then educated further by fine-tuning on smaller, more specific language tasks. So BERT could also learn from themselves over time too. And some interesting facts about masked language modeling. So as known as the closed procedure is a kind of sampling or potential readability influence, which has been around for a very long time. The BERT architecture analyzes sentences with some word randomly masked out and attempts to correctly predict what the hidden word is. And the purpose of this is to prevent target words in the training process passing through the BERT transformer architecture from the inadvertently seen themselves during bidirectional training when all of the words are looked at together for combined context. That's a kind of improvement of unidirectional nature of RNN. So it avoids a type of erroneous infinite loop in natural language machine learning, which would skew the word's meaning. So this is my inference, and that's all my presentation. If you are interested in search engine, machine learning, and artificial intelligence, you could dive into it while this inference. So that's all. Thanks for listening.